Okay, why don't we spend I don't know, 5 minutes recap what we learned last class. You have this already, but doesn't hurt to draw it again. It probably will help you remember it a little bit better. So we talked about DNA strand like this. Of course, they are supposed to be in the double helix form, but to make it easier to draw and to understand, we're just gonna draw two lines here. DNA strands have directionality to it, and we use numbers to represent them. What numbers do we use? 5 and 3, that's it. So it's 5 prime to 3 prime, and then on the other one, it would be 3 prime to 5 prime. And what happens is when you need to copy the DNA, which is something that you need to do every time you make a copy of the cell, then you have to create a replication bubble. Okay, so it opens it up like this so that we can gain access to the nucleotides that are in the DNA strand. And we use that as a template to build the missing half. So once again, this is 5 prime, this is 3 prime, and then it will be the other way around on the opposite strand. In order to open up the replication bubble, we're going to need an enzyme to do it on both ends. And what is the name of that enzyme? Very good. So that unzips the DNA, creates the replication bubble, and it will expand horizontally so that you can unzip the rest of the DNA. Now, as you unzip the DNA, I told you, you know what? I probably should move this a little bit. Give me 1 second. Now, this thing is actually, hello. Let me just erase a little bit of this. 5 prime to 3 prime. Now, this is, of course, all wound up in the double helix as I showed you before, like that. Okay. So, what happens is when you are unzipping the DNA, the tension is going to build up in the strand right here. And in order to remove the tension, we're going to need another enzyme, don't we? And what is the name of that? It's gyrase, that's right. Okay, same situation on the other side. If you want, you can draw that as well. And then you're gonna need a gyrase right here. If you missed last class, the recording is online. Make sure you go watch the recording, okay? Now, we want to keep the strands apart. So there are these special proteins that will bind to the separated strands and prevent them from coming back together. They are called what? Okay, good. Sounds like you guys have been studying. And then we're gonna have these primers, right? We're gonna have these primers. Primers are created by primase, and it's kind of like an example for the polymerase 3 to follow through, right? To continue to build upon. And if you follow the numbers over here, you will see that because we have the 3 prime here. So on the opposite strand, it will be 5 and 3. And the polymerase 3 can only build in the 5 to 3 direction, right, for the new strand. And since this strand is being built continuously, we would call it the what strand? That's right. So it's the leading strand on the top here, and then it will be leading strand on the other side for the bottom. And as we open up more of the bubble, you will need to have additional primers in place so that you can continue to build them. Okay, so that's pretty much, the key stuff we were talking about last class. Again, this is the leading strand, which is being built continuously and towards the fork. And on the other side, we have the lagging strand. Similarly over here, just the other way around. And we have a name for these fragments. What are they called? Very good. Okay, so these are Okazaki fragments. Which are only found on the lagging strand and not the leading strand, right? That's all we've learned in 5 minutes. Uh, any questions before I tell you the rest of the story? Okay. So hopefully you have this with you. What we're gonna do next is we will zoom in on this region. Okay, we're gonna zoom in over here. And let's take a closer look at what's happening. Now, don't forget these lines, they represent DNA, which means they are nucleotides. And then I'm just gonna write a few nucleotides here, okay? They're just randomly created. It doesn't really matter. And so we have a primer here, which we use uracil instead of thymine. Now, the actual primer is going to be longer in real life, but we're not gonna write hundreds of these things. Bless you. And then we have the polymerase 3. That's going to be building this thing, right? And over here, you're gonna have another primer. So far, nothing is new. It's exactly what we have been talking about. So just copy that first, and then I will explain further. All right, so here is my low-tech animation to help you understand, all right? So this calculator here, this is DNA polymerase 3. DNA polymerase 3. So number 3 is gonna come here, and then it's gonna start building the nucleotides, right? It's just gonna continue from the primer, right? So it's gonna put what is it gonna put? It's gonna put a C, a G, a T, and then an A, right? Nothing difficult. However, when it approaches the primer that's in front of it, it's actually going to fall off. And then it's going to go and ask for another DNA polymerase. And this time it's DNA polymerase 1. Okay, so number 3 is going to build, but when it gets to the primer, it's going to fall off, and number 1 is going to take over. It's going to take away these primers. Okay, so replace the A with another A, G with another G. No big deal. But when it gets to the U, that's where the replacement is really going to be meaningful, right? It's going to take away the U and replace it with what? T, right? Because we're building DNA, not RNA, right? And then we replace it, the C with the C, and then it's done. Okay? So once again, 3 will do its thing, but once it gets to the primer, it'll fall off, and then it will recruit number 1. Number 1 cannot come on its own. It needs number 3 to tell it to do it. All right? I want you to remember that point. It's going to be important for something else we will discuss in a bit. Okay? Number 3 falls off. Number 1 takes over, and then takes away the primer. Got it? Okay. Now, I don't know how to draw all that on the diagram here, but I will try. Okay, and here we go. As DNA polymerase 3 approaches the RNA primer, DNA polymerase 3 is replaced by DNA polymerase 1. Is it the wrong color? Oh, that looks like the wrong color. All right. So remember, this is only um, assumed in area here, right? So actually what happens is this parent strand, it's gonna continue with the bubble, right? And so like it's longer, right? Which means there's gonna be another DNA polymerase 3 coming from here, which will replace these primary eventually. You understand that? And this is not the end of the line, right? That's what I'm trying to. Sure, please.
We can only these two side products of DNA polymerase 1 and DNA polymerase 2, or we have DNA polymerase 2.
Great question. Yeah. So like where is number 2, right? We see 1 and 3. I'll answer that in a bit, okay? Yeah, just hang on. All right, and just one last thing. After the primer is replaced with actual nucleotides, AGTC, then the C at the end needs to form a covalent bond with the G in front of it. In other words, all these Okazaki fragments needs to be stitched together. It needs to be glued together. And so there's one last enzyme that is required to do this. Okay. At the end, Okazaki fragments are joined together by running out of color here. It doesn't matter. You choose whatever you want, okay? By DNA ligase. In English, ligate means to connect things together. So ligase is an enzyme that connects things, connects the Okazaki. Okay, that's it for the process. Like I said, I'm not going to ask you to describe this on a test or quiz, but you will need to know the functions of the enzymes in order to answer some of the questions. All right. Your quiz is not until next week, so we have some time. Yeah. Can I move on? Great. Oh, I don't even have the PowerPoint open. Just give me a second. All right, this is a professional drawing of what I was trying to do in the notes. But as you can see, it's the same kind of information. Let's see if you can identify some of these things. What do you think number 2 is? Helicase. Excellent. Okay, how about this? These little circle balls. Yeah, single strand binding from here, right? Now there is actually a mistake here, I think. Yeah, there's a mistake in this diagram. Do you notice where it is? We're gonna give you like a minute to try to find the mistake. I'll tell you in a second. Another question. Which one is the leading strand? Top or bottom? Top, because it's being built in one go. And then these are the orthosaccharic fragments, right? That's polymerase 3, ligase, and then the prime. So this here is the mistake. This is 3 prime, right? Okay. On the original. Let's follow it all the way. Okay, and then they had to do like a weird twist to be fancy. And I think that's where they, end up making a mistake. Because if that's 3 prime there, and then you go all the way here, this should be 5, right? So like, oh, let's twist it. Oh, but I forgot to change the numbers. Right. So anyway, it's not a big deal. I doubt anybody would notice if I hadn't mentioned it. But now that I have mentioned it, let's just fix it. Okay. I won't ask you to label something like that on the test either. Okay. So like, don't worry. This is just for you to compare your notes with the actual, professional drawing. All right. So everything we learned so far up to this point is what happens in a prokaryote, right? Which is simpler cells, right? Like bacteria. In fact, the work is done by studying E. coli and how they copy their DNA. We, of course, are more complicated. We are eukaryotes. And our method of copying DNA is similar to what happens in prokaryotes, but there are a few key differences. I will tell you 3 of such differences. Number 1, because our chromosome is longer and it's linear, it actually makes more sense for us to have multiple origin of replications instead of just one. So for prokaryotes, they only open one bubble, and then the bubble expands sideways and they copy all their genetic material. For us, we have billions of base pairs to copy. It would make more sense to open up multiple bubbles and then copy simultaneously at various locations. Okay, so this is the original, and then now we open it up to create several replication bubbles. The bubble will expand horizontally, and eventually it will merge together, right? It's like if I asked the whole class to help me copy a textbook, the most efficient way of doing it would be like you start at chapter 1, you start at chapter 2, chapter 3, and so on and so forth. And eventually, we just put all the work together, right? That's what happens here, right? We start at multiple points, and we can finish faster. Okay, this is in eukaryotes, which is us, but not in prokaryotes. Number 2, second difference, and that addressed your questions. Most of the enzymes in prokaryotes have a eukaryote version of it, but there are sometimes multiple versions of the same enzyme. In prokaryotes, they have DNA polymerase 1 and 3, right? We have additional ones, including number 2, right? And various other versions of it. Sometimes they're called like 3A and 3B, which we don't have to worry about. Okay? The key thing to know is we have the same enzymes, but in multiple forms. Right? Now, this last point is very important. Some of you are starting to, space out, but come back to me, okay? Because this point is going to tie into the next half an hour of my explanation. Okay? Some DNA are actually lost every time we copy our DNA. If we copy our DNA, we end up chopping off a little bit at the end every single time. So it gets shorter and shorter and shorter. This is not going to happen in prokaryotes. It only happens with eukaryotes. Okay? Why? So I'm going to try to explain to you And then I'm going to explain why something like that is problematic, how do we overcome those problems, and implications of that as well. So let's take another note on it. So this note, we're going to talk about what telomeres are. But first, let's take a closer look at the prokaryotes. Now, prokaryotes have circular DNA. This is a bacterium. And inside the bacterium, they would have their genetic material like this.
Wait, are we drawing?
Yes, please. Yeah. This is circular DNA. Our DNA are not circular. Ours are linear. They are straight. They don't loop back on itself. Think of this as like a rubber band, okay? Circular. Now, if you have a hard time visualizing it, I can draw the whole DNA out for you. Okay, it's, of course, much longer than this, but pretty much is essentially what I am trying. Oops. I kind of messed up there. There we go. And these are the base pairs. You do your best, right? You might probably do it even better than me. Okay, so it's a circle. Now I am gonna draw this in a simpler version to help explain the concept. Okay. So that's a double helix. You understand that, right? Just goes all the way around. And I am only showing one strand of the double helix. Okay. Like there would be another one, but it would be too confusing to draw both. You understand? Okay. So look, when the bacteria needs to copy its genetic material, it needs to put a primer, right? And then, the bubble, as it opens more, then you might need to have more primers, and so on and so forth. And then the polymerase 3 will do this, will copy, 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 copy. It will get to a primer, and number 1 will take over, just like we discussed. So over here, same thing. Over here, same thing. The advantage of having circular DNA is that you will always be able to replace all the primers because there will always be a polymerase 3 coming your way. Okay. Over here, this go and it's going to replace that primer. This primer is going to be replaced by, when the polymerase 3 gets here, number 1's going to get on and it's going to replace. Do you understand my point? There will always be something coming from upstream, we say, from above, to replace the primers. Now, if that doesn't totally make sense, like what's the big deal if we replace all of them, right? If that doesn't quite make sense yet, just hang in there. Hopefully I can help you understand. Sure, go ahead.
Say, if we lose some DNA, you specifically mentioned eukaryotes, you said in a process of replication, we are losing some DNA. Does it mean that afterwards we are getting all?
Yes, yeah, hold that thought. That's exactly where the story is going to be going, okay? Yeah, very good. Okay, so for eukaryotes, our DNA is like this. Our DNA is just linear. I just want to make sure, like sometimes I take things for granted. Do you all understand what I mean when I say it's circular versus linear. Everybody get that? Okay, circular is, again, like the rubber band, right? Linear is like if you cut the rubber band and now it's like a noodle, right? Okay. So here, linear DNA. Okay. Now this is where it gets very interesting. I get really excited talking about this. Okay, so let's separate the DNA like this. We have the 5 prime and the 3 prime, 3 prime, and 5 prime. Okay. I'm not drawing the bubble for simplicity. Okay, obviously you're gonna open up the bubble and so on and so forth. You definitely should draw this, okay? Now I'm gonna put a primer here, and then I'm gonna put a primer here. Because once again, the DNA polymerase 3 is unable to initiate the process. That's what the primers are there for. Right? It helps start the process and guide it. When you're ready, I want you to think about which way will the replication go. When the DNA polymerase 3 comes over here and continue building on the primer, on the top here, is it going to go to the left or is it going to go to the right? Just point to the direction that you think is correct. When the polymerase 3 gets here, is it going to go to the left or to the right? Okay. What about the rest of you? Yeah, most of you got it right. It is going to go to the left. Okay. Why is that? Because the DNA polymerase 3 can only build in 5 to 3 direction. Not 5 to 3 of the original, but 5 to 3 of the new one. Okay, so on the top here, if it's 3 over here, then this number must be 5, right? It's opposite. That's why it's going from 5 to 3 towards the left. Okay? So how do we copy the rest of the DNA? Well, I already told you, you are going to need to put more primers, right? And then you're going to have to get more primers as you open up the bubble. And then what happens is polymerase 3 will come and build and build and build and build like that. And here is the problem. All right? Here's the problem. Polymerase 3 will build, 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 build. When it gets to the primer, it falls off. Polymerase 1 comes and removes the primer and replace it with DNA, right? That's what I told you. So that's okay. This is going to be replaced with DNA, no problem. Is this going to get replaced with DNA? Of course, right? Because then the polymerase 3 is coming, it's going to fall off. Number 1's going to get on and replace it, right? Okay. What about this last bit over here? Is that going to get replaced by DNA? No. Why? Because this is the end of the chromosome. Nothing is coming from upstream. We don't have a number 3 coming along. If number 3 doesn't come, there's no signal for number 1 to get on. Okay? And as a result, this last part of the RNA is not going to be replaced with DNA, and it's just going to fall off and get lost. And that's why when we copy our DNA, and our DNA being linear, we will lose the end every time we copy it. Okay? Similar situation with the other side. This time we're going to the right. And of course, we will have more primers. And then it will go like that, right? So the problem is these ends, the RNA primers are not replaced. So they were gone. They were gone forever. Every time we copy, we cut off the ends a little bit and a little bit and a little bit. Do we understand? Oh, I don't know if you guys know this was left in the classroom after the beetroot lab. It was at the back. Is anybody? It has to be this class because it was on the table after the beetroot lab. No? Okay, that's weird. I don't know what's inside, but it's probably all rotten now. Leave it there. All right, are we ready for the next exciting part? I promise it's going to be very exciting, okay? All right. So that's a concern, right? Like I would be concerned every time my cell divides and then I lose a bit of DNA. And DNA, of course, are very important. It gives instruction to our cells and tell them how to function and how to make proteins, right? So how do we protect the ends of DNA? And that's where telomeres comes in. Okay? Telomeres are located at the ends of the chromosome. Okay? This picture just shows you what I try to draw it out for you, right? Like you do not replace the end primer and you end up losing it. Okay. So how do we protect the ends of the DNA? We use these non-coding DNA sequences called telomeres, and they are repeats of TTA GGG. It's TTA GGG repeated 50, 100 times, and they are located at the ends of the chromosomes. The sole purpose of the telomeres is to protect the DNA that are located at the ends of the chromosomes. Think of them as the plastic thing that is at the end of the shoelaces. Okay? Without the plastic thing, the shoelace is going to fray and get damaged, right? Okay? And that's what happens. These are chromosomes, and the part that lights up at the end, that's where the telomeres are going to be located. All right? So think of it like this. If I tell you every time you tie your shoelaces, you have to cut off a little bit of the plastic thing. Okay. So I tie my shoes, I have to chop that off. I gotta change the color here properly. Okay, you gotta chop this off. Next time you tie your shoes again, you gotta chop it off, chop it off. And eventually, if you tie your shoes enough times, you wear it enough times, and you're gonna chop off a lot of the protection, right? So if you want to wear it one more time, might not be a good idea because now you're going to start chopping your actual shoelaces, right? And that is exactly what happens. When our cell divides, sure, because of the limitation of how DNA replication occurs, we are losing the ends, but the ends are non-coding telomeres, okay? So it's not going to affect us too much. But if the cell divides too many times, okay, after 30 divisions, 40 divisions, maybe the telomeres will be critically short now. Okay? It's too short. It's like we're running out of the plastics. If you copy one more time, we will start cutting into actual DNA, and that is dangerous, right? So when the telomeres are critically short, the cell actually is not permitted to divide anymore. Okay. Sorry, what's that? Yeah. So what happens then when the cell is having critically short telomeres is exactly what you were saying. The cell becomes senescent. Okay. Senescent means old, right? So as we get older, the pool of senescent cells in our body starts to increase, right? Because our cells have been dividing for so long up to a certain point, and they won't be allowed to divide any further. And as the pool of these old cells increases in our body, that's a contributing factor of why we age. Does that make sense? Yeah. So like if you're 40 years old, 50 years old, your cells have been dividing for all this time, right? Then, wound healing becomes a little bit slower. We don't really grow anymore. In fact, you don't really grow after adolescence anyways, right? And part of the reason is because of this critically short telomeres. Do you understand? You have a question? Good.
So if someone could create one of these that could last.
Oh, that is exactly the question I was looking for. Excellent. Okay. Yeah. Hold that thought. I was waiting for that. I have a slide for it. Okay. But before that, let's talk a little bit about Dolly. Okay. Anybody know who Dolly is? What Dolly is? You guys heard of it? Hands up. Yeah, obviously there's sheep, but there's there's a picture right here. Okay. But Dolly, if you didn't know, is the first cloned mammal. Okay, cloned mammal. A clone means genetically identical. Okay, if they were to clone me, I don't know why they would, but if they did, then you would have the exact same me. Okay, but it's not like the movies, right? It's not like if you clone me, then you're gonna get the same adult version of me. It would start off as a baby that's genetically identical to me, and then it will grow up. Probably not gonna look exactly like me, because there's environmental factor that change how your genes are being expressed and so on and so forth. But I'm going to spend a little bit of time explaining to you how Dolly was created. And this actually relates to the telomeres that I was telling you about. But first, let's do a quick game. How many sheep do you think it took to create Dolly? Now, I don't mean all the failed experiment where the sheep die and stuff like that. In the successful version of this experiment, how many sheep do you think it's required to create a clone sheep? Just put up your fingers. Okay. I have one, I have two. Anyone else? Very conservative guesses here. Change, yeah, change your mind. One, okay. Two. Anyone else? I'm curious. Anybody go higher than two? No? Five sheep? Okay. All right. All right. It's very interesting. So let's find out. Okay, let's find out. So you can copy this. It's good information for you to know. Okay. Everything's gonna come together. All right, so first we're gonna have sheep number one.
Copy this?
Yes, yes, yes.
Oh,
Yeah. If you don't like drawing, you can just go like this, okay? Sheep. Okay. Yeah, sure. Dolly, okay? Dolly, there we go. That's not a very sophisticated sheep, guys. Okay, like I'm sure you can do better. Anyway, this is sheep number one. Okay. And what they did was they took, oh, by the way, this is an adult, okay? Adult. They took a somatic cell from an adult sheep. A somatic cell is a bodily cell. Okay? All the cells in your body is considered as a somatic cell, except for the sperm and egg. Okay? Sperm and eggs only have half the genetic materials. Somatic cells have the full set of genetic material. Okay? How many chromosomes do we have again? 46, that's right. 23 from mom, 23 from dad, right? So our somatic cells would have 46 chromosomes. Our sperm and egg would have 23. So they took a somatic cell from the adult sheep. Okay, so I'm not sure what cell they took, doesn't matter. This is the nucleus with the genetic material inside. And then the next step is they took, they extracted, doesn't matter, extracted the nucleus. Okay, so there we go. We have only the nucleus with the full set of genetic information. All right, so that's our sheep number one. Okay, so here is the second sheep. Sheep number two. And from sheep number two, they extracted an egg. Now, someone was confused in my other class. They were like, I didn't know sheep lay eggs. I'm like, no. This is not like not like chicken eggs, okay? Like it's like mammals, they have eggs too, okay? So they took the egg from the sheep, and the egg, of course, has nucleus, but only half the genetic materials, right? And then what they did was they removed the nucleus and got rid of it. So in a sense, they only, I'll say, removed nucleus and only kept the shell, okay? Like the cytoplasm, the organelles and stuff like that. So we only have the eggshell. All right, tell me what they're gonna do next. We got a nucleus with no surrounding, and then we got a shell with no nucleus. That's right, they're gonna put them together, okay? And they do this under the microscope, all right, with like micropipette stuff like that. So the next step is going to combine these two things. Add them together. So you have the egg with the full set of genetic materials. This simulates the process of fertilization. Normally, the egg has half the genetic information, and it requires the sperm to supply the other half to make the full set, right? But now, the donor, the sheep number one, from the somatic cell, it already has a full set, and then you put it into the egg. So the egg is now kind of fertilized, if you would. You with me so far? Okay. Now it's time to bring in sheep number 3. What do you think the job of sheep number 3 is?
Carry.
Excellent. And what do we call people who carry babies for others?
Surrogate.
That's right. So number 3 is the surrogate sheep. Okay, so they're gonna implant the egg into the surrogate sheep. It's gonna carry it to full term, and then that's how they got the baby sheep, Dolly. Okay, smaller. There we go. Okay, yeah, that's my next question. So Dolly was created with 3 sheep. Which one is the clone from? Show me a finger. Is Dolly a clone of 1, 2, or 3? Show me the fingers. What about the rest of you? Come on, continue. Okay, good. It's number 1, right? Because number 1 is the only one that supplied it any genetic material, right? Okay. So 2 is only supplying the eggshell, no genetic material. Number 3 is just surrogate, provides the womb for the baby to grow, right? No genetic material. Yeah.
Can they just use one?
Yeah, you know what? Someone actually asked me the same question yesterday. I don't know the answer. Maybe it was too much. I don't know. But they decided to use 3. Okay. And here's the thing. Okay, this is how it relates to what we're talking about. Dolly only lived for 6 years before it died, which is half the life expectancy of a normal sheep. Okay, why is that? It's not because the experiment was a failure or if there's any kind of medical situation that caused this to happen. The reason is the egg, the DNA that was taken from sheep 1. Sheep 1 is an adult, right? So when we extracted the cell from it, the telomeres in the DNA has already been dividing for some time up to that point of extraction, right? If the adult sheep was like, I don't know, 8 years old or something like that, then those telomeres would have been shortening for 8 years, right? And so even though when Dolly was born, biologically, it's age 0, it's a baby, but on a genetic level, it's the same age as sheep number 1, right? Because the telomeres are already short when it was born. So it doesn't have as much time, as much room to divide any further, right? So the cell becomes senescent sooner than it otherwise would if it was a naturally born sheep. Do you guys understand that? Okay. If they take the cell from like a younger sheep, then maybe Dolly was able to live longer. Okay? But because they took it from an adult sheep that has been living for some time now, that's why the telomeres were short. Are we together? Okay, now this should lead you to think of another question. Okay, anybody have a good question for me related to what I just told you? It's okay. Oh, sorry. Oh, what have I done? Okay, any questions though? Any questions about us? About humans, reproduction? Come on. Okay, some of us have kids, and if you don't have kids, maybe you plan to have kids. When do you plan to have kids, guys? Like some of you, I don't know. Random
When?
question. Sure, yeah,
Okay, I want to get married at 24
sure.
and then first kid 26.
Okay, excellent. Okay, so you know, if I'm just gonna use you as an example, if she decided to have kids at 26 years old, her DNA would have been shortened for how many years? 26 years, right? Because then your cell, you have been growing, your cells have been dividing, right?
And so the earlier that you have,
Okay, hold on.
Oh, sorry.
So wouldn't that be a problem, right? Like if I have a kid at 30, my cells have been divided for 30 years, then wouldn't my children inherit short DNA? And wouldn't they have shorter life expectancy? That's what you're gonna ask, right?
yeah.
Like, and then what about their kids, right? Isn't human race gonna become extinct because we pass on shorter and shorter and shorter telomeres? Are you guys with me?
Yeah.
Okay, so that's logic, right? Okay. Fortunately,
Oh.
that's that's not the problem. That's not the situation. Okay. And that's because of this next thing. Now, this is where things can get confusing. Okay, so stay with me here. What I have been teaching you so far is telomeres. Okay, Telomere, right? Telomeres. Those are the plastic things at the end of your chromosomes, right? They delay the erosion, right? They delay the shortening. But when we want to have kids, we need to create the sperm and egg in the body. And the cells that makes the sperm and the eggs, we call them germ cells. And so two kinds of cells in the body. Somatic cells, which are like the normal kind, and then germ cells will become the sperm and the egg. Okay, don't confuse the word germ, sounds like, dirty bacteria stuff. No, these are cells that will become the sperm and the egg. And within the germ cells, there is a special enzyme called telomerase. Okay, remember all the enzymes we learned so far ends with ASE, right? Helicase, gyrase, right? Polymerase. This one is telomerase. The job of telomerase is to reset the telomere length when we produce the sperm and egg. So even though we have kids in the 30s or 35s, even though our telomeres are short, but when we produce the sperm and the egg, the telomerase will reset the length, and we give brand new copies to our children when we pass them on. Does that make sense?
What about those animals that like combine out of their like how am I gonna put it? You know
Just say it as it is. It's fine.
yeah, there's like this lion that mated with the tiger.
Oh yeah. Okay, that's different. Right? That's like different species coming together, right? So that's a different story.
Is it like a sort of
No, they are actually infertile because they are two different species, right?
Yeah.
So they're not able to, for a different reason. Okay, so without telomerase, you see the telomeres get shorter and shorter and shorter, eventually critically short, cannot divide, right? It's gonna take more than 3 cycles, but you get the point. With telomerase, it's gonna stay intact, right? Okay, now usually this would lead to another question in some people, and I'm just gonna tell you what it is, okay? So, looks like the problem with aging is our cells are no longer allowed to divide, right? And that's caused by shortening of the telomeres. Okay? But now you're telling me we can prevent the shortening by having telomerase. So what's the next? Yeah, please. Exactly, right? And that's a logical thing to think about, right? How come we don't put telomerase in all of our cells? Then we can have beautiful skin and live forever, and everybody's going to be happy, right? Well, that's actually not an ideal situation. It turns out telomerase are turned on and expressed in cancer cells. Okay, remember I talked to you about HeLa cells a long time ago? HeLa cells are the cancer cells that was taken from that lady, right? The ovarian cancer, and it was able to grow forever in the petri dish, right? One of the reasons it became immortal is because they turned on telomerase in those cells. Okay, so when cancer develops from our body, basically it has found a way to activate telomerase. And by activating telomerase, when the cancer cells divide, they don't have to worry about having telomeres that are critically short. They can just keep on resetting it and resetting it and resetting it. And as a result, they can keep on dividing and dividing virtually indefinitely. Okay? So having telomerase being activated in all our cells is not actually going to let our cell live forever. I mean, it will let them live forever, but not in the way that we want it to be. Okay, cancer cells live forever in the sense that they can keep on dividing and dividing. Okay, and so what happens is researchers are trying to explore inhibiting the telomerase so that they can stop the growth of the tumor. Okay, if they keep on coming back, well, maybe we can knock out the telomerase in them, and that would cause them to no longer grow. And combine that with like surgery, chemotherapy, maybe we would have a potent treatment. Yeah.
So is it true that like everyone has cancer cells, it's just if you have too much, it's bad, right?
That's a good point. Yeah. Actually, we'll learn about that next semester. Your immune system actually keeps those cancer cells in check, right? They say we randomly generate 4 to 5 cancer cells every day, and you have a special type of cells called the natural killer cells in the body that would get rid of them. Okay. But when that system fails, then then the person would develop cancer. But this is not
Because if it's already bad, like chemo just gets rid of it, but can't it?
come back, right?
Keep on.
Yeah, so that's why there's like relapses, right? And it can come back, right? Because at the end of the day, if you just leave behind 1 or 2 cancerous cells that you're not able to get rid of completely, then they could just grow back. That's right. But this strategy is not without risk or downside. It's entirely possible that when someone goes on telomerase inhibition, they might become infertile, right? They might not be able to have kids, right? Because remember, we actually need telomerase to produce reproductive cells. Okay, so no strategy is 100% risk-free, and that's why it's so challenging to come up with effective treatments for cancer. All right, so that was a lot of information. Let's see how much you've learned. Go ahead. Is that an answer? Yeah, okay, good. Try again, please, at the back. Yes. Yeah, good. Good. Yes. Try again. Not quite. Yes. Good. Okay. So remember, we talked about 3 differences, right? Number 1, we need to have multiple origin of replication. Right. So that's the right answer. Number 2, there are multiple versions of the same enzymes. And number 3, our DNA gets shorter every time we divide, but not for the prokaryotes. How about this one? Good. Mm-hmm. What's the English word for connecting, guys? Yes, okay, ligase, okay? To ligate is to join. So ligase connects the Okazaki fragments together. Next one. Yeah. Yeah. That's good. Anyone else? Very good. Anyone else? Yes. Anything?
Like at the end of them, the two fragments, that's what. So it's about like, yeah, in this.
No, no one else? Okay, yeah, this is DNA polymerase 1, okay? Right, that's the one that replaces number 3, and then it will remove the primers, right? Okay, last one.
The answer was the one.
The answer is, yeah, D. D, yeah, type 1. Okay, how about this one? Last one. Okay, good, 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 good. Not quite. Mhm. Right, so telomerase are needed to re-lengthen shortened chromosome, right? Every time we have to reproduce and make the sperm and egg, you have to reset, re-lengthen the telomere. Okay. Telomerase does not prevent cancer development. In fact, I told you telomerase actually is one of the reasons why cancers are immortal, right? The TTAGGG is the repeat on the telomeres. Okay? Don't confuse the two. Telomeres are the DNA, the plastic thing. Telomerase is the enzyme that makes them again. Okay. All right, break time. Let's take 5, and then we'll continue. All right, we're gonna go and move on to the second half of the lesson. For the first half, we have been talking about how to copy the DNA, and the mechanism of DNA replication. But that's for only the first half of cellular reproduction. Okay, if you recall, when we start with a single cell, which once again we have 46 chromosomes, the first step to do before you allow the cell to divide is DNA replication. You need to make a copy of all 46 chromosomes, and then you will allow the cell to divide, and each of the daughter cells, we call it, would also have 46 chromosomes. Okay, so this process of division is called mitosis. And that's what we're going to be learning for the rest of the lesson. Okay, let's take a closer look. Oh, sorry. Yeah, go ahead. I'll let you go at 2. Okay, just hang in there. Right, we're almost there. We actually ahead of my other class, so. Now, we learned this already. This is not new. First time we talked about cell theory was in lecture 3, but I just want to put it up here to kind of remind you what it is. Now, over here, the third part of this cell theory states that all living cells come from division of pre-existing cells, right? We, at some point, were just one single cell. Okay? When the sperm and the egg came together, it created the first cell called the zygote, which from that single cell comes trillions of cells. That makes us up at this moment, right? So in the process, all that cell division essentially is mitosis. The purpose of cell division includes replacing lost or damaged cells. If you have a cut, then you lost some cells. And as the wound heals, you need to replace the damaged and the lost cells through cell division. Growth and development, right? As we grow from childhood to adult, we gain a lot of extra cells. That too came from cell division. We humans do not rely on mitosis to reproduce. Okay, we do another kind of mechanism to reproduce, which we will learn in lecture 8. But some organisms rely exclusively on mitosis to reproduce. We actually call those kinds of reproduction asexual reproduction. Humans, we do sexual reproduction. Sexual reproduction requires two individuals, okay, males and females, and the fertilization of the egg by the sperm. But for asexual reproduction, it's just one individual. Okay? If you have a single amoeba, it's able to split and become two. Right? Did you guys know starfish can reproduce asexually? If you have starfish and then it breaks into two, you come back later, you will have two starfish. Okay. Of course, there is like a minimum amount of biotissue you need. Right? Someone once asked me this in class, like, oh, it's good to sell starfish as a business that you only have to buy one and keep on breaking and you will, have unlimited supply. Doesn't really work like that. Okay, like there's again have to have minimum amount of biotissue, and there is a limited number of times the organism can sustain these kind of divisions, right? But plants can do it. Okay, plants is very easy to asexually reproduce. My mom does this, right? She grows these aloe vera and then she would repot it and then she sells it online, right? For like $1 each. And I always tell her, it's not worth the effort, okay? Like all the soil and all the watering, that costs you more than $1. And then she's like, oh, it's okay. It's just for habits. Anyways, if you want aloe vera, let me know. I can hook you up. Yeah, so this is the advantage is only one individual is required. It's relatively fast and it doesn't really require much energy. An amoeba can divide under ideal condition within the hour. Right? But for us, if we want to reproduce and create have child, it takes at least like 9 to 10 months, right? Okay, so that's it. And that's just to have the child come out and then you got to raise them and so on and so forth. So it's very energy demanding. The main disadvantage of asexual reproduction is low genetic diversity. Right? Every single organism that comes from the original one will be genetically identical. And whenever a population is genetically identical, it's very vulnerable and susceptible to some kind of catastrophic wiped out, right, of the population. Think back to the beginning of the pandemic, right, when COVID-19 came out. People got sick from it and people died from it. However, there are also individuals who seemingly are not particularly affected by it, right? They caught the virus, but they don't get very sick, right? And part of the reasons for that is because of genetic diversity, okay? All of us are genetically quite different, and so some of us are more resilient to certain kind of diseases, right? If we have low genetic diversity in the population, if all of us were the same genetically, and that virus comes and kill one, then it's going to kill all. Right? So this is a major disadvantage for asexual reproduction. Now there is a catch here, which we'll come back to it and talk about it at the right place. Now this is just to show you and refresh your memory of how DNA in its naked form, it's just a double helix, but we learned that it actually can package with other proteins and becomes the chromosome, right? Okay. So when it's just in the nucleus, it's in the form of chromatin. That's like a yo-yo I told you about, right? With the proteins and you wrap the DNA around it. However, when we are trying to move the genetic material around as the cell is dividing, we need to pack it up even further. And that's when we get to the chromosome. Okay? We learned this already. The chromosome and chromatin are the same thing. It's just that the chromosomes are more compact compared to the chromatin. So let's talk about the chromosomes in humans. Okay, chromosomes are basically made of DNA, and you know now. So you and I are not related, at least I don't think so. So on a DNA level, what percent of our DNA would be the same? What do you think? Give me some percentage, some numbers. Okay, if we look at my DNA and look at your DNA, compare all the ACTGs, what percentage would be the same? Throw me some numbers. Between me and you. 15 or 50? 15%, okay. Anyone want to be more, higher or lower? 50, okay, so now 23%. That's a really precise odd number.
You're saying, wait, like, what are you saying this is the DNA?
Your DNA and my DNA. What percentage would be identical? 98%. Okay, anyone else? What's that? 2%? Yeah, we're nothing alike. You know what I mean? We are 99.9% identical on a genetic level, okay? Not just between you and I, between you and every other humans on this planet, 99.9% identical. If you compare all the ACTGs, 99.9% will be the same. That might be shocking, right? That might be shocking, but that's because we are both humans, okay? To make a human, with arms and legs and, eyes and ears where they're supposed to be, require a certain core genetic instruction, right? And that's what that 99.9% is. Okay, you can Google it if you don't believe me. Okay, the 0.1% difference is what accounts for the difference that we see on the surface. Yeah.
How, like, if you have siblings, wouldn't it be more?
So yeah, when they say we are like you and your siblings are like 50% identical, we are talking about 50% of that 0.1% difference. Okay. Now it's getting very math. So 99.9% is all the same. Okay. So of the small percentage that's different, right? You can still have closer relationship with your kins than others, right? So we're talking about that small differences, like how much more can you share in terms of similarity. Do you guys understand that? Okay, here is another one. Okay, someone Google this, right? If you want. What about us and chimpanzee? Okay, chimpanzee at the zoo. I don't want to find out, right? Okay, someone Google it. What percent of DNA is shared between humans and chimpanzees? Throw me some numbers if you don't want to. 73. Okay, 73. 80. 95. We're getting close. 100. No, even you and I are not 100. 98. Yeah. 99. Okay. Yeah. So we're getting somewhere, right? Okay. I think is 94%. Okay, 94%. Okay, between humans and chimpanzees. Okay. So we have 46 chromosomes. They actually have 48 chromosomes. Okay. So we are both primates, right? So we are actually more similar than we like to admit sometimes. Okay. Anyways, very interesting stuff for you to ask your friends.
And people have different hair colors, and there's so many things that are different about everyone.
Yeah.
How does that account for 0.1?
Yeah, and that's the amazing part, right? I guess one way to think about it is you think about different cars, right? Think of a Civic, Honda Civic versus like a Toyota Corolla. Okay, are they same or different? They are different, but not in the sense that it's different from like a car compared to a plane, right? So that's what I'm trying to say. To make a car, there are like certain things that you can't really change. Like you need four wheels, you need the engine, and that 99.9% is what makes the human, right? To have two eyes and not have like furry limbs and whatever, right? That it's just yeah.
Ask you a question.
Sure.
How many percent are really like bananas?
How many people what?
How many percent?
How many like bananas?
Genetically.
Genetically, how?
From
Oh, what percentage between humans and bananas? Oh, I don't know. Yeah. Maybe someone ask ChatGPT. Okay.
60%.
How many?
60%.
60%. Okay. Wow. Next time. You know that for a fact, or you just like trolling me? Okay, we will fact check that one. Okay, so next thing. All right, come back to this. Humans, we have 46 chromosomes. I told you already, okay? 23 pairs. 23 from mom, 23 from dad. You will hear me say that again and again to help you remember it. Now, of the 23 pairs of chromosomes, 22 pairs of them, we call them autosomal chromosomes. You need to know this name, okay? Autosomal chromosomes, or autosomes for short. These are chromosomes that would determine everything about us except for the sex. Okay? So your hair color, your blood type, how many fingers you have. Do you know people can have 6 fingers? Anybody know that? Yeah, it's called polydactyly, right? It determines whether your earlobe is dangling or attached, right? All these external features about you is going to be determined by 22 pairs of autosomes. Okay? The sex, whether you're XX or XY, that's going to be determined by the sex chromosome. Okay? So females genetically are XX, and then males genetically are XY. So I want to ask you, who determines the sex of the baby, of the child, the mother or the father? That's right, because the father is XY and the sperm only either carries X or carries Y, right? If the one carries the Y fertilizes the egg, then it's going to be a boy. Otherwise, it's going to be a girl, right? Okay. My grandmother is very traditional, okay? So I have 2 daughters, as you know already, right? So every now and then she would sit down next to me and she would, quietly whisper into my ear. It's like, how come your wife is not giving you boys? Okay? You only have girls. And then I would try to explain to her, it's not her fault. It's actually my fault, right? It's the man that determines the sex of the baby. And it's like, no, that's not true. I would know. I have 4 sons. Right? I was like, no, that's not how it works. Right? And here's another thing she would say. Right? If you have another child, I know it's going to be a boy because you already have 2 girls, right? Next one must be a boy. And I'm like, no. It's it's like flipping a coin, right? If you flip the coin twice and you get heads and heads, what's the probability of getting heads next time? 50%, right? These are independent events, right? Okay. What happens in the past is not going to affect the future, right? Okay. So, anyways, if you didn't know that, now you do.
So, okay, because with my family, on my dad's side, I guess, like all of his cousins and everyone, they all have girls. So all my cousins are all like, there's like, I think there's like 1 or 2 boys or whatever, but every single one of them has girls.
Sure, right? And there's that, and that's okay, right? There are not necessarily, right? It's the same thing as like why someone wins the lottery and not me, right? Even though chance is slim, but it could happen, right? Yeah. Okay. So the point, sex chromosome is XX or XY. Now, another thing to kind of understand is the number of chromosomes is not really related to the size of the organism, okay? We have 46, sure, but something much smaller, like a goldfish, they actually have 100 chromosomes, okay? So there's no correlation between the complexity of the organism and the number of chromosomes they have. Plants can often have hundreds, if not thousands, of chromosomes, depending on what kind of plants you're looking at. Okay, so we have 10 minutes, and I just want to take one more note with you, and then we will be done. This is a short note. So this is called cell cycle overview. Now I'm gonna do a pie chart, and I know you guys have learned pie chart in math, so or computers. So here's a pie chart, and we can think of the pie chart as like the life of a cell. Right? So how does the cell spend its lifetime? Well, typically the cell would spend 90%, much of the big piece of the pie, 90% of its life in what's called interphase. Right? Interphase, 90%. So that's like, all the I'm not going to be able to do it nicely, but you can. 90%, this whole piece here. So during interphase, the cell is just doing its normal function. It's growing, it's gathering resources. Okay. And interphase is going to have certain key events that I want you to know. So for example, as the cell is growing, here, maybe I'll put it down for you. Okay, this is just performing normal functions. Okay, growing, gathering resources. If it's a muscle cell, it'll be contracting. If it's a liver cell, it'll be, detoxifying things and whatnot. Whatever its function, it's going to be doing it in the interphase. Yes.
As one cell. So as cell divides and going into the folder, right? Folder is right. Well, different cells should get performance.
Yep. That's a great question. So I am oversimplifying things here. Yeah. But when we get to lecture 10, you will see that we actually have these things called stem cells, and they don't just straightly divide. Okay. They can choose to become different things. Okay. So stem cell is like this class, right? Some of you will graduate from this program and become practical nurses. Some of you might go into massage therapists or whatever, right? So they specialize. Right? Even though we all came from the same place. All right. Okay, so this whole thing that I'm highlighting, okay, that's gonna be the interphase. Now, within interphase, like I said, there are a couple of key points I want you to know. Right here, this is called G1 checkpoint. And then over here later on, we're gonna have G2 checkpoint. It's like, getting the license in Ontario. You gotta get your G1 and G2 before you can have your license. All right. So what's going to be happening in these checkpoints is that it's like a checklist that your cell has to go through to make sure it is ready to copy the DNA and it's ready to divide. There are lots of things they have to consider. For example, in G1 checkpoint, you want to check for size and volume of the cell. If the cell is still very small and it has room to grow, then you don't necessarily want to divide yet. Right? In fact, you might not have enough material and cytoplasm to divide. Okay, so you want to check that. You have to check for the quality of DNA. Specifically, are there any DNA damage? Are there any errors that we need to fix? And also, we just learned earlier today, are the telomeres critically short? Okay, so you need to check the quality of the DNA. So example, errors, damage, telomere length. Telomeres, M-E-R-E. And then resource availability. Do you actually have the nutrients, the ATPs, or do we have enough ATPs? Do we have enough nucleotides? Remember, you're building 3 billion base pairs, right? Do you have the ACTGs? And so you got to check all these things. Okay. And if the answer is no, then the cell is not allowed to progress to the next stage. Okay. It depends on which one gets failed. Like if it's just a size problem, then maybe wait it out. Eventually it's going to be okay. But if we have DNA damage and errors that cannot be replaced, that cannot be repaired rather, then what happens is the cell might be pushed out of the cell cycle and it would go into growth arrest. Okay, it might become senescent or trigger apoptosis. Does anybody remember what apoptosis mean? Programmed cell death. That's right. Okay. If the cell has too much damage, like let's not keep it around. Okay. Triggers cell death. Maybe the damage is fine, but then the telomeres are too short, becomes senescent. If the size is not big enough, or we don't have enough resources, then let's just put a pause. Right? We're not growing yet, but we could resume when the right environment and conditions are. Is it okay? Do you need me to read something? Which word? No? So what if everything is good? If everything is good, then we're gonna move on to the next phase right here, which is called the S phase. Okay, S equals to DNA synthesis. Okay, or copying. That's all the stuff we learned so far. You know, the helicase, the DNA polymerase 3, right? This is the actual part where you are going to be copying all your genetic materials. Right? And at the meantime, your cell is still performing its function. Once you finished copying all the genetic materials, we got to do a second check. Okay, what do you think we're checking for this time? You just copy 3 billion base pairs. If you just finished typing a 3,000 word essay, what are you going to do before you hand it in? Yeah, you got to proofread it, right? Okay, and that's exactly what we need. With the G2 checkpoint, we are once again going to check for quality of copied DNA. We no longer have to worry about resources. We no longer have to worry about the size and stuff like that. We already checked that. And the telomere length is irrelevant now because after the copying, we're not going to shorten it anymore, right? So that's basically that. And once again, if we found errors and then it cannot be replaced, it's possible that the cell is going to get ejected from the cell cycle. And then that's it. Okay, so over here, we're just going to put growth, and then growth again. And then finally, when it's ready, this 10% of the time, that is where mitosis will take place. Mitosis, the actual cell division. And that is what we're going to talk about next week. All right? I don't know. We should be able to finish lecture 6 on Tuesday. It should take the whole class, but in case we finish early, please also bring lecture 7. Okay, just in case we have time. That's it. Thank you. I think we are changing the clock this week as well, right? Right. So yeah, make sure you're caffeinated when you come to class next week. Bye. No, you're losing sleep this week.